great to be here in the land of what I think of as the land of natural language research. In fact, I was really interested, yesterday I was at the cognitive science department because I'm also interested in human language processing. And I was really struck by how dominant a theme natural language understanding is in the cognitive science department here too. So I guess, like Johns Hopkins University, I'm also interested in both human language processing and computer language processing. Today we'll talk about computer language processing. And really the talk is motivated by a simple observation, which is that us humans, unlike most machine learning programs, learn many things. And we don't get turned off after we process one data set, hopefully. Instead, we learn many things over days and weeks and months and years and decades. You know, we learn to walk and talk. We learn to add. We learn to count. Then we can learn to add. Then we can learn, once we learn how to add, we can learn things like algebra. And after we learn algebra, then we can learn things like calculus. And in parallel with that, we're not just learning this kind of narrow-minded mathematical stuff. We're learning to walk and ride a bike. We're learning physics, and oh yeah, learning that physics helps us learn calculus better, and learning calculus helps us learn physics better. And so there's a lot of, there are many functions, to put it in machine learning terminology, that our brains are learning. And there's considerable synergy in the learning of those different things over our lifetime. And there's a kind of staged curriculum, if you will, stage sequence of things that we learn. We don't start by learning calculus and later learn to add. It's the other way around. And so I'm struck and saddened by the fact that the field of machine learning, which I hold dear to my heart, doesn't learn that way, doesn't even try to build computers that learn that way. Instead, we primarily talk about machine learning as a process where there's some function we're trying to learn, like maybe a mapping from emails to spam, yes or no. We get a data set, we give it, we approximate that function from that data and totally out of context of anything else, and then we turn it off and use our spam filters. So there's the observation, and the simple question is, well, why don't we start looking at what it would mean to build computer programs that learn over days and weeks and months? And so that's what we've been trying to do, and the we is a considerable list of colleagues of mine at Carnegie Mellon, including several faculty like William Cohen, Noah Smith, Christos Faloutsos. And so the work that I'm going to present here is actually due to a number of people. So what's the problem specifically? Well, we decided here's the problem that we're going to try to address. I want to build a system that learns to read the web. And the inputs to the system are going to be an initial ontology. By that I just mean a definition of a bunch of categories and relations we want to learn. So we might say we're interested in categories like universities, and if we are, we'll give a dozen training examples. Johns Hopkins, Carnegie Mellon, Harvard University, a dozen of those. We might say we're interested in emotions, and we'll give a dozen emotions: happiness, sadness, anxiety, frustration. And we might say that we're interested in certain relations among these categories. Not only people are we interested in organizations, but maybe which person founded which organization. And again, we'll give a dozen examples of that. Bill Gates founded Microsoft. Larry Page founded Google. So the input is an ontology and a handful of examples labeled by us for each of those. The web, and occasional interaction with human trainers, which in practice has turned out to be about 5 minutes a day, except during finals week. And then the task is to, given those inputs, to have the system run 24 hours a day, and each day do just these two things. Number one, extract more facts from the web to populate those categories and relations we said we were interested in. And number two, this is actually the more important of, well, this is just as important. Learn to do task number one better each day. And how would you know that? Well, the evidence would be if the system could go back to the same text that it looked at yesterday, but today extract more facts more accurately. Then we'd say, well, yeah, it has learned to improve its performance at number one. So that's the spec. That's what we would like to have. And we figure if we had a system that could do this, then we could just turn it on and wait 15 or 20 years and we'd be very happy. All right, now we have not solved this problem. But what we do have is a system that's now 2 years old. It's been running 24 hours a day for 2 years. It has an ontology that, I guess this slide is a little out of date. It's up to about 750 categories and relations. Oh, I see. Yeah, we input about 600 of those, and there are about 100 that it has since added on its own. It has a cache of 500 million web pages that it's downloaded. And Google has given us permission for this system to make 100,000 search queries a day against the Google search engine. And the result so far, after 2 years, is a system that has about 15 million extracted, I could call them facts, but they're not all correct. And it has different confidence in them, so let me call them beliefs. It has about 15 million beliefs. That it's considering at different levels of confidence. So what are those? Well, here's a sample of what I mean by a collection of beliefs. So it believes, Nell believes, for example, that the Maple Leafs play hockey. It believes that their hometown is Toronto. It believes that Toyota is a company that created the Prius, and so forth. So each one of these triples, Toronto's city paper is the Globe and Mail. Each one of these triples is some belief that Nell holds in its database, its knowledge base, with some degree of confidence. And together they form a vast network of interconnected beliefs about the world that it's reading about. Now, it's not all this pretty. This is actually a subset of Nell's knowledge base. But when I created this slide, I decided not to include incorrect beliefs. So this is a subset that happens to be correct. And if you look at the 15 million beliefs Nell has, there are different levels of confidence. It has what we'll call high confidence in about 1 million of these. And among those million, the accuracy is around 85% currently. So it's not perfect, still makes plenty of mistakes, but it's starting to do pretty interesting things. Pardon me? Can you repeat those percentages? Sure. It has 15 million triples that it's considering. Of those, about 1 million are ones that it assigns high confidence. And of those 1 million, they're about 85% correct. Yeah?
You tested it against your average passerby on the street?
No, we didn't. But we tested by giving a sample of these beliefs to Mechanical Turk, and so that's a little bit like asking people on the street.
Okay. And how does it compare to your average passerby?
Well, it knows a lot more about professional sports than I do. And about obscure rivers in Eastern Europe. So, and it knows less about machine learning than I do. So
are all these beliefs that were extracted from text, or it's text plus reasoning?
Text plus reasoning.
Okay.
Yeah. So
Beliefs are based on transitivity.
yeah, primarily these are extracted from text. I wish I could give it next year. I hope I can give a talk that says 50% were extracted by reasoning. But today it's more like 5%.
And when you're rating the confidence, does that look at plausibility under reasoning? Like I can imagine.
Oh, yeah. Yeah.
This kind of triangle looks bad. This kind of triangle looks good.
Yes, definitely. So the confidence is based both on how certain it is that it's extracted from text, this belief, and also what additional confidence it might have from inference of that belief from other beliefs. Okay, so let's you can go look at this yourself, but there's a website here. Wait a minute. That shouldn't happen. We should go to a website if I do that. I want to show you, you can browse this. There it is. You can browse this website yourself, but part of what we've decided for the project is that the knowledge base will always be online. So you can see today Nell's number of... Oh my.
Just drag it over.
Man. Hang on. Yay. Okay. Too many features in my browser. Okay, let me do it this way. Apologies for the logistics of screen management. Let me refresh that. Maybe, yeah, good. This is easier to read. So here's a random sample of 10 beliefs that are in the knowledge base. In fact, if you don't like that random sample, we can just get a different random sample. And so this gives you an idea of what's in there. So let's just go through these. This says, thinking add monkeys is a cognitive action. I have no idea what thinking add monkeys is. It's probably well, who knows. South Williamsport Police Department is part of the government. Oatmeal is a grain. Probably a misparsed noun phrase. Adam Dunn is a Mexican person. Sneaker is a kind of clothing. New York World is a newspaper in the city, New York City. KUSP is a radio station in the city, Santa Cruz. Bread can be served with honey. Home is an animal that preys on turtles. Something's wrong there. Matt Cassell is an athlete who led the Pats. Okay, so we get the idea. It's not perfect, but it has a quite diverse collection of beliefs that it's considering. And any of these that we're actually interested in, we can drill down on. Like, let's look at sneakers. Perhaps. It doesn't seem to be helpful. Okay, I think I may have some internet connectivity.
It's slow from this material.
Okay. Well, maybe let's not browse then, but I encourage you to browse on your own. You got a feeling for what the sample of beliefs looks like, but if you browse, you can click on any one of those, and it will tell you all of the beliefs that it has about that entity. So, for example, you could click on sneakers. Hopefully it believes sneakers is a kind of clothing. Maybe it believes that sneakers go with T-shirts. Those would be typical kinds of things that it might believe. But it will also give you the justification for those. But I can see this maybe is not working for us. So let's go back to the slides. Okay, so...
Let me ask you another question.
Sure.
So the 600 odd entries in your ontology, there, I guess these are triples where the nature of the relationship is already asserted in the ontology?
Yes, yes. So these, all of the relations that you see, all of these triples are ontology, are relations mentioned in the ontology.
Okay. But
So
you
like,
said it discovered another 700, another 100, 150.
on its own, right.
So the labels for those were inferred by now.
By now, yeah, yeah. So, right, so most of these we put in by hand. By the way, it takes about 15 minutes to add another one. We keep trickling them in if you have some relation or category you're interested in. Basically what you have to do is say, well, here's another category. It goes here in the hierarchy of categories, and here are a dozen examples. So you have to give a dozen noun phrases, or in the case of relation, a dozen noun phrase pairs. And then you just come back a few days later and see what it has done with that. So it's easy to add new things. And as we will get to, Nell is now adding some new kinds of relations itself.
Browser, is there a color coding or something that says this is a relationship that Nell discovered?
No, but if you look for, if you go to the browser and you look for relations that begin with inverse of X, then those are automatically named relations which Nell made up itself. So you'll see things like inverse of musician plays instrument. And musician plays instrument is an example of a relation that Nell added. Yeah, sorry about, maybe we'll come back at the end and see if we can get on the net. But what we really want to do is talk about what's inside Nell, what are the algorithms, and what have we learned really about trying to build this kind of a system. And we've learned that it's not easy, but I think we've come up with 3 good design principles, 3 good ideas that are responsible for Nell's competence to the degree that it's competent right now. And the first of these ideas is about how to do coupled, semi-supervised, multitask learning. And so let's start there. Let's start with that idea. Suppose that I ask you to build me a system that, like Nell, is going to get a handful of examples of some category. Let's take cities as an example. And let's say I give you these 4 labeled training examples of cities. And now you have to come up with an algorithm that will learn to extract more cities from the web. So one algorithm you might come up with, this is in fact the first one we tried, would be, well, I've got all this unlabeled text on the web. Why don't I search for those 4 noun phrases and find the kind of context in which they occur? Maybe I'll find mayor of Cupertino, live in Seattle, and so forth. And I might think, well, therefore, I'll use these phrases to go look for more argument ones that I will presume are also cities. And if you do that, it works kind of. So you'll find mayor of San Francisco, but you will find live in denial. It's out there on the web. You will find it. And mostly you'll find cities, but you'll pollute your pool of presumed cities somewhat. And then you might say, okay, now we'll take these 7 presumed cities and we'll find more phrases. And you will. But the problem is this works great on the first iteration, but if you run it for 1,000 iterations, it just kind of blurs. It gets defocused. Okay. So you might think, well, that's not such a smart algorithm. But it's actually a great algorithm. I defy you to come up with a better algorithm if that's the problem. See, I'm giving you very little information. I said I have some secret category in mind, and the only thing I'm going to tell you is here's a sample of 4 members. And you don't know what category I have in mind. It could be cities that begin with a consonant. It could be the union of cities and personality traits. And there's no reason for you to say that this is a bad outcome. So the problem is not with the algorithm. The problem is with the framing the question. You don't want to try to build a semi-supervised learning system that has such weak initial information to learn from. It's not going to work. Or if you can make it work, you're a better researcher than I. But I believe you won't be able to, because I think fundamentally the problem here is that this is an under-constrained framing of the problem. So good idea number 1 out of the 3 for Nell is don't even try this. It's too hard. Don't try to learn a single function that maps from noun phrases to some category like city or person. It's just under-constrained. Much easier will be to force your system to learn simultaneously many different functions that are coupled. Remember, you learned physics at the same time you learned calculus, and it actually helped. At least it did me. And so this is good idea number 1 in Nell. And when we changed from trying to do this to trying to do this, all of a sudden the system just performed incredibly better. And the bigger we grow the ontology, so that there are even more functions that Nell has to learn, the better it works. So it has this very nice scaling property that the more you demand that it learn, the more diverse things you demand it to learn, the better it does. We still work with noun phrases. The truth is, now Nell is learning half a different types of knowledge, but the first one that it learned was to classify noun phrases. Okay, so let's look at exactly why this helps. So think about it this way. If I go back to trying to learn one function, say from noun phrases to labeling it a person, yes or no, Boolean variable, Boolean output. And suppose I use the phrases that I find this noun phrase in as the features, then if I'm doing a supervised learning approach to trying to learn this function F1 from noun phrases to yes or no, it's a person, then I will typically set up my learning problem as an optimization problem where I'm trying to pick the parameters of this function, maybe the weights on these features, for example, to optimize, to minimize the sum over the labeled data that I have, pairs of noun phrases and known labels about whether they're a person. I'll just try to minimize the difference between what F1 predicts and the true label yes or no person. And that's standard supervised learning framing of the problem. But if I have two functions that I'm learning, suppose I have a second function that's also trying to predict whether a noun phrase is a person, but it's doing it, in this case, with a different view. This function is ignoring what's the phrase in which we find this noun phrase. Instead, it's looking inside the noun phrase. Does this noun phrase end with the three letters SKI? Well, if so, then it's probably a person. Does it contain the token UNIV period? If so, it's probably not a person. Okay, so here's an example of two different functions which Nell tries to learn. And when you introduce that second function, you qualitatively change the problem, because now the objective you're trying to optimize is, of course, use whatever labeled data you have to minimize the errors over that labeled data for function F1 and F2. But also, now, here's the key thing. All of a sudden, because we have two functions that are trying to do this, and two functions that are trying to do this, we now have a third term we can introduce in the objective function, which essentially is to demand that these functions not disagree with each other. So all of a sudden, now we can sum over every single noun phrase that we find on the web as an unlabeled example. And we can require that when we learn that F1 and F2, that they agree. So we take a noun phrase like computer. System doesn't know whether that's a person or not, but it does know that if this thing thinks it's a person, this thing should think it's a person. So there are legal joint assignments, and there are illegal joint assignments. And so that's the key. And once you get this idea, which is a pretty simple idea, namely that if you have several redundant functions that are trying to predict the same thing, then all of a sudden every unlabeled example becomes a constraint on the joint choice of parameters for those two functions. Okay, now once you get that idea, you say, well, why stop at 2? And we don't. So for example, and now there's the third view that comes from Richard Wang's PhD thesis on the SEAL system, which also tries to label noun phrases based on features of particular web pages on which those noun phrases appear. And all three of these functions make independent errors because they're making their estimates, their predictions based on data that's pretty much independent. And so as you increase the number of functions that make independent errors, you decrease exponentially, you decrease the probability that they will happen to agree by chance despite the fact that they're wrong. So as you increase linearly the number of independent functions that are being coupled, you improve exponentially the probability of a chance agreement. And so if you get real agreement, in fact, you're probably right. And in fact, there are theoretical results that show you can actually use the disagreement rate of independent functions over unlabeled data to estimate the true accuracy of those functions, or at least to bound the true accuracy of those functions. Okay, so that's good idea number one, but once you have it, why stop with just 3 different views for predicting whether somebody's a person? And now we're also trying to learn not just which noun phrases refer to people, but also which noun phrases refer to athletes, coaches, sports, teams, emotions, cities, etc. So we can also couple the training of, instead of having different views of the noun phrase predicting the same label, we also have the same noun phrase, but we're predicting Boolean labels of many types. And we know from the ontology certain constraints on the joint assignment of those labels. For example, the ontology states that an athlete is a kind of person. And therefore you know that if one classifier says that this noun phrase refers to an athlete, and the other classifier says this is not a person, then you know one of them is wrong, in the same way that the multiple views gave us this synergy. I see a couple hands, but let me finish this part, then we'll come to the questions. So now we put these two things together. We have many labels we're predicting. We know some constraints about their joint assignments. We also have multiple views, as we saw, phrases, morphology, wrappers on different web pages. And so we get this network where every one of these black arrows is a different function that Nell is learning. And they're coupled both in terms of the requirement on agreement based on different views and agreement based on the joint assignment, consistent joint assignments. And then there's one more piece of this. It doesn't end there because this just covers learning to classify noun phrases. But Nell is also learning to extract relations, like person founded company, person plays musical instrument. And for each of those relations, when we insert it in the ontology, it's a typed relation. The relation person-founded company is a relation between noun phrases of type person and noun phrases of type company. Athlete play sport is a relation between athletes and sports. And so we can take the relation function extractors, which are essentially classifiers of noun phrase pairs. Bill Gates, Microsoft, yes, positive example of person-founded company. And those relation classifiers of noun phrase pairs have to also be consistent with the individual classifiers of the types of the involved noun phrases. Okay, so when you put this all together, there are a couple thousand of these black arrow functions that Nell is learning, and they're all wrapped up in this network of consistency constraints. And every time you add one more consistency constraint, remember that objective function where we summed over the unlabeled examples? You get another constraint in your objective function that is being optimized as you learn this collection of parameterized functions. So that's good idea number one in Nell. And the implications of this, I think, are pretty interesting. The implication of this is we shouldn't have 700 categories and relations. We should have 70,000. The more we can develop a more intricate nest of these different functions coupled in different ways, the better we're going to constrain that semi-supervised learning problem that Nell's up against. Yes? Oh, that's good. Yeah, if you didn't hear it, the question was, is there a bias variance trade-off here? Is there a problem with having too many constraints? If the constraints are wrong, then yeah, then you're going to regret this. We actually find it not difficult to state what we think are pretty correct constraints. You know, athletes really are people. founder of company really is a relation between people and companies. So, so you're right that there could be a danger if the constraints are incorrect, but the ones that we put into the ontology, which are essentially subset, superset, athletes are kind of people, and argument types. And there's a third kind that's in there too, which is mutually exclusive. So we say fruits are mutually exclusive from emotions. You can't be both. You can still have a token. Well, let's say fruits are also mutually exclusive with companies. That's true despite the fact that there are tokens like the token apple that can refer to a fruit and can refer to a company. But that's a matter of polysemy. That's not a matter of the correctness of the constraint that fruits cannot be companies. And Mel is dealing with polysemy as a separate issue that it's trying to learn about. So the bottom line is we think the constraints that are in the system are actually correct. Yeah?
So is there a slide coming where like all these functions that you know described in a couple slides prior are sort of explicitly modeled as marginals?
No, but there's a slide that tells how we actually do this. So let me do that slide. How would you train such a system in practice? So there is a problem with training such a system in practice. It's scale, right? So in an ideal world where we had infinite computation, we would use EM to train this system, right? EM is this nice algorithm where we iteratively take all these unlabeled noun phrases and noun phrase pairs and use our current model to assign labels to each of those noun phrase and noun phrase pairs for each of our functions and relations. And then that would be the E step. Essentially, we get probabilistic labels for every function over every possible input to the function. And then on the M step, we would just retrain all those functions using those probabilistic labels. If we did that and ran it until convergence, we get to at least the local maximum likelihood estimate of the parameters and the labels for the data. And that would be a good algorithm. But it doesn't work in practice because the numbers are too big. So in the E step, we have 20 million noun phrases, roughly. And so we have 10 to the 14th noun phrase pairs, roughly. And it just takes too long to write down the labels for 10 to the 14th things. So that's a problem. On the M step, we have other problems, which is there are a lot of these phrases that occur around noun phrases. And so each function has 50 million or more parameters, and you've got to apply them to 10 to the 14th. You see the problem. So as a practical matter, we can't just apply EM. So we use an algorithm that I would characterize as E prime M prime, which goes like this. On the E prime step, well, like the E step, we're going to label, we're going to assign labels with different confidences to noun phrases and noun phrase pairs, but not to all of them, not to all 10 to the 14th. In fact, we only do this in a most confident first kind of strategy. So on every iteration of this E prime, M prime, we're going to label just the ones we're most confident in. And that number is going to grow per iteration. In fact, we can add 250 new noun phrases per category and relation on each iteration. Okay, so that gets us away from the 10 to the 14th problem. And then and this is important, notice the output of the E prime step is the knowledge base. The knowledge base is that set of triples with associated confidences and justifications. That knowledge base is the result of the E prime step. And then the M prime step is just, well, then we'll retrain each of these different functions that's involved. And we cut some corners there too because, you know, there are 50 million phrases that occur out there on the web. And again, we only incrementally add in the ones that are most useful on each iteration. Okay, so this algorithm is a lot like EM, but you have to cut corners just because of the scale of the problem. And so we cut it in a most certain first, least certain last kind of strategy. Yeah?
Is there any real difference here from the traditional co-training?
Is there a difference between the co-training paper and this?
It's been a while since I've looked at the paper. The paper has two tabs, one of which says here's why it should work, and the second says this won't really do.
Right. So this is somewhat more sophisticated than that algorithm because this one is really taking into account confidences, whereas the first algorithm that we used co-training for, we basically said when you label something, just take the most confident K things and label those and throw them into the pool, but then ignore their confidences. This one is actually looking at some of those confidences. And this one's also dealing with the joint assignment thing. The original co-training paper had multiple views, but only one label. And this thing has many labels. Right, but it's quite similar. It's basically co-training on steroids. It's the natural expansion of co-training to do this kind of many functions. Yep?
So would you say that you're learning in linear time, or is it getting slower and slower because this still doesn't keep up with the input?
Yeah, let's see. It takes about a day per iteration, a CPU day per iteration. It's going a little bit slower because the knowledge base is getting bigger, but it's not slowing down horribly. And we know how to speed it up. And we could parallelize it more than we do.
Okay, so I guess there are two. One is, theoretically, theoretically you would expect to get slower. The sense that you are observing that it's getting a little bit slower over time, but not a whole lot. But you can
Right. And the one reason it gets slower is it has these 15 million triples that it's considering, but it used to be 5 million. And maybe next year it'll be 25 million. So just the number of candidates that are around there, if you go through them linearly, obviously that's going to slow down. We do various indexing and heuristics to say, well, this one probably didn't change very much, and so we're not even going to look at it this iteration. And so there are things that you can do to make reasonable heuristics to reduce what you have to look at on each iteration. But we haven't really pushed that very hard. I'm actually kind of glad that Nell doesn't learn faster because we're trying to also keep up with what it's doing and improve it fast enough so that it doesn't run off the rails, to be honest. But we could parallelize this and get a big speed up, which we're not doing at the moment. Okay, so that's good idea number one in Nell. If you're going to do learning mostly unsupervised, then don't try the hard thing of learning one function at a time. Do something much easier, like learning a lot of functions that are coupled, because you have a more constrained learning problem. You're probably going to do better, and all of our evidence confirms that. Okay, it leads to a very simple architecture. Here's the base level architecture for Nell, which is basically we have the knowledge base, and on the E step, each of these different types of learners goes through all of the functions that they've learned for all of the categories and relations and contributes more proposed candidate beliefs. The evidence integrator looks at those and decides what confidence it's going to assign to beliefs and which beliefs it's actually going to put into the knowledge base. And then that's the E step, and on the M step, they all just retrain themselves. Very simple, and you could add more modules like this to the system if you have ideas about other ways. Maybe using hyperlinks on web pages could be a better way, a good way, a fourth way of learning relations, for example. Well, we could just slot it in here. And it would be another thing that helps to co-train the growing knowledge base. All right, so what actually gets learned? Well, it's good that I have this slide since the browsing didn't work very well. So here's just a sample of some of the phrases that Nell has learned are good probabilistic indicators for the relation person, place, sport. So for example, baseball autographed by Mickey Mantle is a good indicator for Mickey Mantle plays baseball, or football autographed by Joe Namath, or golf legends such as Arnold Palmer, and so forth. Okay, so these are the kind of phrases that it learns. And it has now hundreds of thousands of these phrases that it has learned. They're all in the knowledge base. If you go browse, go to the meta information associated with the relation, you can see the set of phrases that it has for any given category or relation. I mentioned that it's also using the character strings that make up the noun phrase. So what kind of stuff gets learned there? Well, for example, the first 3 lines here tell us some of the features and the logistic regression weights for those features that decide whether a noun phrase refers to a mountain or not. And so that first feature says, well, if the last word in the noun phrase is peak, Pikes Peak, then positive, big positive weight, that's probably a mountain. If the last word is mountain, Himalayan mountain, then again, positive weight. If the first word of the noun phrase is mountain, negative weight. Mountain bike. Okay, so that's the kind of internal structure of the noun phrase. Or visual art movement. If the last 3 letters is ism, it's positive indicator that this is a visual art movement, but not if the first 4 letters are journalism, or not if the first ones are Buddhism. So one of the surprises that we've had is when we put in this kind of morphological component to now, we didn't actually believe that it was going to be useful as widely as it has turned out to be. We thought it might be good for names like Polanski, ends with ski. But we found across many, 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 many categories, this is actually a very useful, independent way of making a judgment. And then I mentioned that the third way had to do with finding specific URLs. And this is the work, again, of Richard Wang, who was a PhD student working with William Cohen at the time. But here's the kind of thing it learns. Let's look at like this last one. If you're trying to extract the relation book author, then you should go to http://lifebehindthecurve.com and look for patterns like, essentially these are list elements on some list on that page, where you see X by Y indicates that X is probably X is probably a book and Y is probably the author. So it learns these URL-specific HTML extraction patterns. And where does it get the training data? Of course, this is part of the E prime M prime algorithm. So it gets the training data from the current knowledge base, and it goes out and looks for pages that mention what it believes to be pairs of books and authors. And once it finds a page that mentions multiple of them, it looks for, is there some HTML regularity there? And if so, then that's what it does.
So the way these URLs were identified was automatically searching for a number of book author pairs.
Right, so this is one way we use the 100,000 queries a day against the search engine to find those. And then we cache these pages into the growing.
The weights are, is it linear scale or is it kind of a log scale?
These are actually logistic regression weights, so it's a log linear model. But each of these learning methods is actually a different learning method. Like this one that's learning these wrappers for web pages, it's not a logistic regression function. It's doing some kind of heuristic confidence thing. So in this architecture, it's not essential that you have a homogeneous approach to learning. You just need to have modules that can train themselves by looking at the knowledge base and then can suggest stuff with different confidences to the knowledge base. So, yeah?
You have some extra parameters that sort of affect how these individual models are combined? Or how, when you combine, things from the...
Yeah. So in the architecture you saw there was this evidence integrator module. I'm not proud about what it does, but basically it just assumes these guys are all making independent errors, which, given the nature of these things, is not a horrible assumption. But we're looking to improve that.
There as well, right?
Pardon me?
In principle, you could ask the parameter
Yes. I think we can do better there, and I hope we do, because that's not the part of the system that I'm particularly proud of. Yeah?
Don't you really get slammed
By NP? We do. The noun phrase apple is a horrible word. Yeah. So let me get to some of these issues. So what I've done is I've shown you the baseline version of NEL, which is what it was about a year ago. And now as it's learning, we keep noticing problems and trying to make it learn better as it's growing. So I want to get to some of these other issues. But yeah, noun phrase ambiguity is a horrible problem. So I mentioned there were 3 good ideas in NEL. One we've just talked about, which is if you're going to do semi-supervised learning, couple the training of many functions. Well, if that's a good idea, it leads to good idea number 2, which is, well, if coupling the learning of many functions is good, how can we get more coupling constraints? And the answer in NEL is we learn them. Because once you've got a collection of 15 million beliefs about the world, you can data mine those to find out empirical regularities in the world that you're reading about. So NEL does that in a couple ways. One is that it learns probabilistic horn clause rules, like this one, that says athlete X plays sport Y with probability 0.93 if athlete X plays for team Z and team Z plays sport Y. Okay, it's common sense. You and I knew that. But NEL knows that now because it's read enough instances of these 3 relations to notice that there's a striking predictive regularity there. And so NEL reads and then data mines, essentially learns probabilistic horn clause rules from the collection of beliefs that it's read. And then it uses these to infer new beliefs, which effectively is adding new coupling constraints to its learning procedure. So here are some examples of rules that has learned. Like team plays in the NHL if they won the Stanley Cup. Or city X is in state Y if X is the capital of state Y. And it's in the U.S. I don't think you and I wouldn't have thought of putting the second clause in that rule, but NEL did because the rule works better if you do. Maybe that's patching over some kind of reading mistake that it's systematically making for cities that are non-American cities. And you see this a lot in the empirical regularities that it finds. It patches, it has stuff in it, and you say, why is that there? Quite often it's there to cover up some blemish in its ability to do some particular kind of reading. Okay.
Well, presumably the only states are in the USA in the sense of state. Is that what's going on?
No, because it has states like Punjab province.
Yeah.
And then there are cities in that state too. And
It might be a naming convention thing because I think the U.S. is a little different in the sense we very regularly write city, comma, state when we write addresses. It's not common in the rest of the world. So one of the cues that helps it find city and state might be that pattern.
might be that.
That doesn't apply to us.
Yeah. So there might,
Something like that.
yeah, there could be some reason why it's easier for it to read U.S. cities, including the fact that they're mentioned more frequently. The way NEL reads is by aggregating statistics, like you'll look at all mentions of Pittsburgh and Pennsylvania when it's trying to figure out whether city and state applies to that pair. It won't just look at one sentence, it looks at them all and it aggregates the statistics about the different phrases that cover those. And therefore, it's much better at learning properties and relations that are mentioned many times on the web. And it's very poor currently at learning properties and relations that are mentioned once on the web. It doesn't. But that could also have something to do with the error rates that we're getting.
So this leads me to ask how much NEL knows about what it doesn't know. One reason that it might restrict this to USA is this rule would make correct deductions about cities in India, but it doesn't know enough about cities in India. So often when it tries to use this rule to predict them, it says, I don't actually know that that's true.
That's true.
It only validates it.
Yeah, actually, that's a plausible argument, but it's not true for this particular learning algorithm because it doesn't penalize it for predicting things that are unread. So
You mean is consistency on the unlabeled data right or wrong?
you would, although it's not actually checking on that. You do want that. That's right. You want some kind of consistency checking on these inferences. But we don't know how to manage the computational complexity of that, so we don't do consistency checking when we apply the rules. Okay, so it also makes mistakes. Here's some bad rules, or rules you and I would call bad. It believes with very high confidence that Team X plays in the NBA if they play basketball. My high school basketball team doesn't play in the NBA. But they'll have 35 positive examples and 0 negative examples of that rule. Why? Because it preferentially is good at reading popular things like professional sports teams, and it's not very good at reading about less frequent things. So it's not true of the world, but it's true of the world that Nell is able to read about. So, and there are other mistakes. So what we do at the moment is we human vet these rules before we let Nell go crazy with them. And that's one of the high-value ways to use the 5 minutes a day of human interaction. Okay, so let me just finish this off by saying, so I brought this up by saying, well, if coupling functions is a good idea, how can we improve it? Well, if you think about it, these rules are precisely that, right? This rule is a new coupling constraint among these 3 particular relations that contributes a new constraint on the joint assignment of noun phrase pairs across these 3 relations. And so just as before, this new coupling constraint allows us to squeeze even more information out of the unlabeled noun phrase data that we have. Yeah.
Like the number 0.93, so that's a correlation.
That's actually its map estimate, its maximum a posterior estimate for the probability of the conclusion given the...
Get them on unlabeled data. Like you collected like how many times by doing whatever relationship that you had, these 2 happens and return, and that also happened.
Right. So it looks at, for all the times that it's read an X and Z and Y that satisfy the preconditions, how often has it also read the conclusion? And how often, and what do you call a negative example? Because there are a lot of things that are true, but you just haven't read them yet. So here's an important part of the algorithm. You will notice that play sport is, well, to Nell, that's a functional relation. A professional athlete, we assume, plays one sport. Mickey Mantle plays baseball. And so it gets negative examples by using functional relations. If it's read that Mickey Mantle plays baseball, then it infers that Mickey Mantle does not play soccer. And for that reason, we've restricted the rule learning to only inferring relations that are functional. And we have some ideas about how to expand, how to go beyond that. But at the moment, this Hornclaw's rule learning is only learning rules that predict functional things. I think there are some things one can do that are based on how statisticians count the number of fish in a pond. That would be very relevant here. And we could talk about that offline, but I think there are some interesting connections there. Yeah. Good. Time is a problem for Nell. Nell doesn't currently know that there is time. But it does know that president of country is a functional relation. And it has read with overwhelming evidence that Obama is president and that Bush is president and that Kennedy is president. So it's got a problem with time. And I have a couple slides on that, but I don't think we're going to get to them. So you guys are a great audience. So let me just refer you to a couple of papers. So Nell itself doesn't yet know about time, but we're doing some work to try to infer temporal scoping on beliefs. And once we think that works well enough, then we'll add it to Nell so that it will assign temporal scopes to different beliefs that it has. But that's a hard problem. That and polysemy are two of the nastiest problems. Let me run ahead and cover it, because there are several things I want to touch on, and I don't want to overstay my welcome or keep you from lunch. And I shouldn't have mentioned that. Never mention lunch to hungry people. But let me just flash through a couple other things that I think are interesting directions that Nell is moving. So these horn clause rules give us one way of learning to do reasoning, learning to infer new beliefs from the other beliefs that we've read. But if you look at the details of that, in practice, even though Nell learns thousands of good rules and uses those, the overall impact on the knowledge base is small. It's got 15 million of these things, and maybe it can infer only functional relations, and only in areas where it's read a lot, like it has a lot of rules about professional sports, for example, as you saw. But overall, that has just like a marginal impact on the size of the knowledge base. And most of the inference questions that you would ask it, it comes back and says, gee, sorry, I don't have a rule for that. So that's not very satisfactory. And we think that to move forward with reading, you have to move forward with reasoning. So recently we've been looking at a very different way of doing reasoning in this knowledge base, which is based on the idea of doing random walks on the knowledge base graph and learning what kind of random walks to do in order to infer specific individual types of relations. And this is the work of Ni Lau, who's a PhD student, working with William Cohen. And there's a paper in EMNLP last summer on this, and hopefully there will be another paper this summer. But here's the idea. It's actually quite simple. It's not a probabilistic graphical model. What it is this idea. The knowledge base is a graph with colored nodes and colored edges. And we're going to do inference by random walks over different types of paths. When I say a type of a path, I mean, for example, we could start at some node, some concept in the knowledge base. We could follow an edge called athlete plays for team, and then when we get to the end of that edge, we could follow a second edge, team plays in league. If you look at that chain, it's a lot like the precondition of one of those horn clause rules that we just looked at. Okay, so what PRA does, which is Ni's system, is it learns the probability of a relation between two nodes in the knowledge base graph using a trained logistic function where the features are the probability of arriving at node Y starting at node X, taking particular types of random walks. So when you put that all together, you get this sort of thing. Suppose we ask, how would Ni's system PRA infer the country that Pittsburgh is located in? Well, it has learned a model, a logistic regression model with different path types. So the first path type says, follow a chain of these three types of edges. So let's go to Pittsburgh and look for, what's the state that Pittsburgh is in? Well, the knowledge base knows. It's in Pennsylvania. Then you follow the inverse of city and state. What other cities are in Pennsylvania? Well, Pittsburgh, Philadelphia, Harrisburg. Okay, then you follow city located in country. What do you get? Well, U.S. So there's no direct edge from Pittsburgh to U.S., but this chain is a pretty good chain to follow if you're trying to figure out what country Pittsburgh is in. And the probability that you end up at U.S. becomes the value, taking such a random walk becomes the value of that feature. And then the logistic regression combines this feature with many others. In fact, here's the second path. We also could follow the path type Find something that's located in Pittsburgh. Well, PPG and Delta. Find what location those are in, and find this country those are located in. And again, we get a probability that we end up at the U.S. taking a path of this type. And these become the feature values that are combined with logistic regression weights. So it's learning a discriminative classifier separately for each type of relation. And its predictions are conditioned on the outcomes of these random walks. And so if you think about it, there's an interesting correspondence between this and those horn clause rules. Each of these chains could be rewritten as a horn clause rule, right? If X city and state Y and Y city and state inverse Z and Z located in country C, then add the relation. But one of the problems with probabilistic reasoning with horn clauses is you're left with the question, how do I integrate the predictions of 15 different horn clauses? To answer that, you have to know the probabilistic dependencies among these different variables in your graphical model. That's a horrible problem. And the inference of it is horrible even if you knew those dependencies. So what we do instead is we just leapfrog that entire problem. We're just going to learn a discriminative classifier that's responsible for figuring out implicitly all those dependencies and their implications. And when we put this together, it actually works surprisingly well. And part of the reason is that the knowledge base is now big enough that it's integrating many different types of paths. So the model for city and state, or sorry, city and country, has 67 different path types, like the ones we saw. Or city lies, find a river that the city lies on and some other city that lies on that river and see what country that's in. So a lot of these kind of probabilistic evidence chains in the graph. And integrating those really helps. Okay, so now once we kind of glommed onto this idea, and this is Nee's PhD work, we started thinking, gee, if this is a good idea, how could we improve on our graph? And around this time, Partha Talukdar, who's one of our postdocs, had just finished parsing, dependency parsing, about 1 billion sentences. And he had these statistics of subject-verb-object triples that occur in those sentences. And so we thought, well, gee, what if we add the subject-verb-object triples? There are about 100 million of them, because the verbs are actually verb phrases. What if we make that graph, which is about text tokens, and did this kind of inference on that graph? What if we integrated that graph with a knowledge-based graph? So we have a noun phrase like Microsoft. We'll link it with a can refer to link to Microsoft the company. Now we have the knowledge about Microsoft the company, but we also have all of these verb dependency relations across the text. And just put that all together. So we're in the process of doing that, but it actually does help. We're doing this initially thresholding those subject-verb-object relations, so we don't even use them unless we get 40 instances of each one. So it's a kind of sparsified version of that graph. But this is actually looking like it's going to be another very useful thing. So for example, when you train it in that way, here's something for inferring which company competes with another company. And now you get, well, if you're asking who does Microsoft compete with, you say, well, follow a company also known as, get another synonym for the company, and then look for that company being the subject of the verb offer and find out what the object is. So maybe Microsoft offers operating systems. And then say, well, find something else that offers operating systems. So in this way, these paths, the graph that we're trying to do inference over, is including both the symbolic level, reified, extracted concepts and relations among them, but also just the raw text corpus statistics with a little bit of shallow parsing that's kind of the sub-symbolic substrate on which all this stuff rests. And it looks like by combining the two of those together, there's more leverage to be had for doing inference. So I'll end the part on inference right there, but I just want to point out it has some interesting properties. It's an anytime algorithm. It's based on doing random walks. So you can say to this algorithm, you've got 500 milliseconds. Tell me what you can tell me. Or you can say, you've got 5 minutes. Tell me what you can tell me. And it'll do more random walks. It'll get more reliable estimates of the probabilities that are the features that are input to the logistic regression. And so I think there's a lot of potential. We're still trying to get our heads around the exact formal relationship between this and horn clause learning. These chains are a restricted form of horn clause. But they take care of this problem that I mentioned before of integrating the inferences due to multiple horn clauses and the interdependencies between those that generally make the probabilistic inference difficult are treated at training time in the discriminative logistic function. If you give me 2 minutes, I'm going to show you one more slide. Just because I did mention automatically extending the ontology. I just want to show you that and mention how it works. So now that NEL has many instances of many of its categories, Mohammed Tahir, one of our students, made up the following algorithm. He said, for every pair of categories in NEL, let's call them C1 and C2, let's just take the known instances of C1 and the known instances of C2. Maybe these are person and musical instrument. And let's find pairs of people and musical instruments that co-occur in sentences often. And we'll look at the text that, the phrases that connect those pairs. And we'll essentially do co-clustering on the noun phrase pairs and the text that interconnects them. And if you find pairs of noun phrases that co-occur surprisingly frequently together, and they use the same kind of phrasings as other pairs that also co-occur surprisingly frequently, then it's a pretty good, that's pretty good evidence that there's some kind of relation among these categories that people are talking about on the web that holds for those particular pairs. So if you do that kind of clustering, what you get are these kind of relations. So if you take the category pair musician, musical instrument, you find sitar and George Harrison, tenor sax, Stan Getz, so forth, and you find these are the top, the 4 phrases that are closest to the centroid of the phrase cluster that goes with those. And then Mel makes up the relation, which is just stealing the phrase that's closest to the centroid. So you'd say musical instrument, master, musician. Or if you give it disease and disease, then you get is due to. Pinched nerve is due to herniated disc. Tennis elbow is due to tendonitis. Or cell type and chemical. Epithelial cells that release surfactant. Or mammals eat plants, or rivers flow through cities. So these are the kinds of relations that NEL is now adding to the ontology. And when it adds it to the ontology, it already knows the typing. That's how it by construction, knows what the types of the arguments are. And it's providing its own seed examples of those relations that come out of that clustering. And so it's providing exactly the information that we would have provided, except for the information about whether it's a functional relation, which we still have to tell it. But other than that, it's basically adding these kind of relations. You see, they're fairly diverse, like athlete injured body part, things like that. So these are the kinds of things that are starting to come out of the system. All right, so I'll end there. And let's see, if I had to make a 1-sentence summary, give me 2 sentences. One sentence is, I said there were 3 good ideas. Number 1, if you're going to do semi-supervised learning, don't try to do it with just one function. It's too hard. Number 2, given that coupling is a good idea, try to think of ways to discover new coupling constraints yourself. They're the same as inference rules anyway. And number 3, which I didn't mention explicitly, if you're trying to build a never-ending learning system, give it a range, a sequence of easy to increasingly difficult tasks for the system to be looking at, to be attempting. And in Now, that sequence looks like initially label noun phrases or noun phrase pairs as relations. Then later, once you got good at that, infer new horn clause rules or new random walk inference strategies. And at the same time, when it got good at the first things, we added deal with polysemy, explicitly represent Apple the noun phrase as a separate entity from Apple the company and Apple the fruit, and explicitly put an edge in there that says Apple the noun phrase can refer to Apple the company. I didn't have time to talk about the algorithms, so that I point you to a paper. And so you see, and then as you get good, you can start to add this kind of knowledge, which you couldn't have done at the beginning. It's like trying to learn calculus before you can add. It doesn't make any sense. But once you start building things up, you actually end up in a position where these seemingly difficult problems become pretty straightforward, just because the system has gotten to a level of scale and competence and knowledge that it can do these things. Okay, that was the first sentence. The second sentence is shorter. If you're looking for a PhD thesis, work on never-ending learning. Nobody's working on this problem. It's wide open. I can't find another person who's building a system like this. I would love to have somebody to talk to. If you're looking for a PhD thesis, think about whatever problem you're working on and ask yourself, what would it be like to build a system that ran for 2 years doing this 24 hours a day? Thanks.